Okay, so let's look at number 1. It says with an initial deposit of $1,000, the bank or the balance in a bank account after T years is found by the following. So if I plug in a certain amount of time in years, I will get a certain amount of money. Now, this initial deposit is $1,000. So this is an exponential function with an initial value of 1,000 and the common ratio of 1.03, meaning that there's going to be some 3% interest that is going to increase the value of this deposit. What are the units of the rate of change of f of t? So we need some kind of units per time. If you're not given units per time, that's usually, this is the rate of change, so we're looking at the velocity. And the rate of change is either going to be secant or it's going to be instantaneous. Either way, it's going to be units per time. Now the units on this is going to be the money. So it's going to be dollars is the units. So dollars per time, the time is in years. So dollars per years are the units of the rate of change. Now I know you have two different rates of change. You have the average rate of change and you have the instantaneous rate of change. This is how we're going to solve these. Average rate of change is y2 minus y1 over x2 minus x1. You learned it back in Algebra 1. Here we say that we have an a and a b value to where f of b is y of 2, f of a is y1, and then b minus a is x2 minus x1. So this is a, this is b. This is an interval. A to b, a to b, a to b, a to b, a to b. We're going to get the y values, which is f of b and f of a, from these established given input x values. And how do we do that? Well, this one's most likely going to be, well, it is. It's a calculator problem. You're going to put these inputs here, right here into this equation, and you're going to see what are the y values that it's going to give you. All right, so the average rate of change is going to come from whatever f of 2 is, minus f of 1.9 over 2 minus 1.9. So you can see 2 minus 1.9 is going to be 0.1. Okay? And then let's go ahead and do this in the calculator just so you can see what I'm talking about. Okay, so I'm going to go ahead and go into the calculator. I'm going to press graph. I'm going to go ahead and make sure that I put the function in as 1,000, 1.03 to the x. So over here on the calculator, it will be 1,000. It will be multiplied with 1.03, and I'm going to raise it to the x power. There's that exponential. When I do this, it will give me values, maybe not graph them per se, but they are going to be accessible through the table. So if I go to the table, Control T, I can look at changing the menu, table, edit table settings, and change this independent variable to ask. And now I'm going to give it all these x values that we have over here, 1.9 and 2. So if I go back to the calculator and I put 1.9 and I put 2, I now have those y values. Those y values, I want to go ahead and make sure that I get as exact that I can from these y values. So I can go and see that this one is 106.9, and it's showing this right here. And then the one, if I go up, this one will show 105 point, and I would say a good one to go to is probably like 6. I would say 6 decimal answers if you see something that is going so far. So we could write 1057, okay, 1057 point, let's go back, 768, 736, 768, 736. This right here was the output from 1.9. So we're subtracting that from f of 2, which is 1060 over here, 1060.9. So 1060.9. This is all going to be over 0.1. Okay, so let's go ahead and put this into our calculator. 1060.9 over here just on our calculate button, 1060.9 is going to be subtracting that 1052 768,736. Now remember, like I told you, you do want to use the as most exact answer as you can, and you don't want to round to the very, very end. You can be safe with 6 decimal numbers. If it continues on like this one is, you would be safe as far as still being accurate. So if you wanted to round, don't round anything less than 6 decimal numbers. Like if you had 0.768, don't put 0.769. That's just too much that you're approximating. Because remember, your final answer has to be within 1,000th of a point. So that's subtracting, and we're going to divide by that 0.1. So divide by 0.1, and we get 81.313. That is our answer for this piece, and we can go ahead and round that part to, or truncate, we could put 0.312, but I'm a rounding kind of person, so I'll go put 81.313. 81.313 is going to be that slope right there. This is the average rate of change that is occurring between 1.9 years and 2 years. Okay, so for the sake of time, I'm not going to do this for every single one of them, but I'm just setting you up as far as how you would do it. It would be 81.313 for this one. You would do the next one. It'd be f of 2 minus f of 1.99. You would still do the same in the calculator, and you would still divide. This one, though, would be divided by the 0.01 because you're even closer. And then this one would be divided by 0.001. This one would be divided by 0.1, 0.01, and 0.001. All the while, still f of b minus f of a would be on top. So now let's go ahead and go to the instantaneous rate of change part. So use your answers to part B to estimate. There's the key word, estimate. That should throw you in the direction of average rate of change, or otherwise known as the secant, which is this that we're doing up here. What is your estimate of the instantaneous rate of change? At 2 years. So I'm basically trying to look at this guy right here. The best thing that you can do is get as close to 2 as possible. This is 1/1000th of a point away. This is 1/1000th of a point away. So to get the best estimate of the instantaneous without truly taking the derivative, you're going to calculate what would this be here, what would this be here, and then you're going to average the two. So whatever you get, so over here we got 81.313, whatever we would get from doing that same process here and here, add them up together, divide by 2, that's what you're going to put. And it's your best estimate as far as the instantaneous rate of change. Just don't forget to put your units as far as dollars for years.